let's talk about energy. When you look on the test notes, you're going to see orbital energy is the K plus U, and this is constant. Now it shows also 1/2 mv squared minus g mm over r. So I want to talk about this potential energy term. We're familiar with kinetic energy already. So the energy of motion, this is just talking about the translational motion, not any rotation as something might be orbiting. Up until this point, when we've dealt with gravity, we said the potential energy due to gravity is mgy. And that's totally valid for any problem where g is constant the whole time. But if we start talking about launching a satellite into space, for example, G is 9.8 near the Earth, but the satellite will not stay near the Earth. So G will not be constant. And so we cannot use mgy in any problem dealing with orbits, dealing with launching projectiles into space, or asteroids coming to Earth, anything dealing with large distances. Now, this equation we get for potential energy goes back to the concept of work. If you remember, work was a force dotted with a displacement. So some sort of force acting with motion, or exactly opposite, parallel to the motion, was equal to the change in kinetic energy. All right, so our force we're dealing with here is gravitational. Now, the negative sign is because that force is always directed towards the Earth or towards the object that's being orbited. It's an attractive force. As long as we integrate between two locations, some initial R value and some final R value, then we are integrating along this radial line. So for example, if we're talking Earth and we're talking a satellite here versus out here, the force of gravity changes on the satellite based on the distance. So our initial to our final, the work is done by gravity though only for motion along this line that radially connects those 2 points. And that's why instead of ds, I'm writing dr, because that is the direction that is along the force of gravity. Now, in terms of conservation of energy, we could say that the net work done was always equal to the change in kinetic energy. But when we talk about gravity, if we just have a straight back and forth conservation of energy between kinetic and potential, delta K is also equal to negative delta U. Meaning if potential energy increases, kinetic energy decreases. So the energy goes back and forth between the two. Since delta anything is the final value minus the initial value, this equals minus U final plus U initial. All right, so making the assumption that the mass is not changing, even though a spacecraft, the mass would be changing. Sorry, this force is R squared. I need the universal law of gravitation, the G/mm over R. Okay, so that leaves me with 1 over R squared dr. I'm integrating from some initial R value to some final R value. So like up in my picture up here. This will equal negative U final plus U initial. Integral of 1 over R squared is going to be negative 1 over R, which we will need to plug in our limits of integration. So on this left side, I'm going to end up with GMM over R final, the negative signs cancel, minus GMM over R initial. So this relates to the change in potential energy. To determine the energy at any given point, we need to be able to plug in an R value and a potential energy value. So let's say my initial R value is some R, some radial distance from the center of the Earth. The U initial will just represent whatever the potential energy is, whatever potential energy our satellite, this object, has when it's at that location. I want to say that our final is infinity. So I've gotten it infinitely far away as I possibly can. Well, if something is infinitely far away, I would assume that it's not going to be attracted to the Earth anymore. And so the potential energy, we could say, is 0 when the object is infinitely far away. By doing that, if I plug these values into this equation I've derived, if R is infinity, then this term goes to 0, and we're defining that potential energy as 0. This tells me that the gravitational potential energy is equal to negative mm over R. Now, capital M and lowercase m, that's the same thing as m1 times m2. I tend to talk about capital M as the object being orbited and lowercase m being the object that is orbiting. Now, this equation is relatively simple to use, but we cannot say that like the surface of the Earth or the lowest point in a problem is defined as potential energy of 0. The potential energy of 0 is infinitely far away. And so we have to account for R, this center to center distance, and account for the potential energy of the objects. Another interesting thing is we end up with this negative sign, which really is hard to conceptually understand. All the negative sign ultimately means is that gravitational forces are always attractive. So objects will always attract each other due to the force of gravity. If you take physics 2, and when we get to the point about electrical potential energy, we find that this energy can be positive or negative, and the difference is whether the charges are attracting each other or repelling each other. With gravity, we only have this repulsion, attraction. So again, I wrote it above, but I'll write it again since it's not showing anymore. When we talk about orbital energy, we're talking about the mechanical energy specifically. So the potential energy plus the kinetic energy. For the kinetic energy, we're just talking about the translational kinetic energy, so moving from one place to another. And then this gravitational energy term is the attractive. It has to be negative, again, because it is attractive. It's just the nature of this inverse square law and the attraction. For anything in orbit, or even assuming no air resistance, no drag, we can say that energy, this mechanical energy, needs to be constant. What this ultimately means is that the kinetic energy and potential energy at some initial location needs to equal the kinetic and potential energy at a final location. So similar to conservation of energy before, we just have a different equation to describe the potential energy. Now, in my equation here, I'm using capital M to represent the more massive object, the object that is or will be orbited, the biggest object involved. Lowercase m is the moving object, the satellite, the asteroid, the smaller object that is either in orbit or potentially can be in orbit. I believe it's labeled with an M1 or an M2 in the test notes. I don't remember which one they label. But just keep in mind, we're talking about the kinetic energy and potential energy of an actual object. And so the object that's in orbit is the one that is in every term. Now, if we go back to what we were talking about with Kepler's laws, we said a planet, as it orbits the sun, orbits elliptically. Now, of course, this is highly exaggerated, but if we think in terms of energy, similar to before, the closer they are, the planet is to the sun, the smaller the potential energy will be. The farther away, the bigger you. Okay, now this one is a little weird to reason out. If we think about potential energy versus distance, r, this equation for potential energy being negative, this potential energy function looks like this. A larger r value corresponds to a bigger u value. A smaller r is a smaller u. Smaller r would be down here. Now we're talking number line values. So if this was, say, -5, this could be -45. -5 is bigger than -45. And so we still see potential energies bigger the farther away from the Earth, or in this case, the planet from the sun. The farther the planet is from the sun, the more potential energy there will be. The closer to the sun, the smaller the potential energy will be. And to swap for that, if the potential energy is smaller, then the kinetic energy is bigger. There's more kinetic energy. Thus, the planet is moving faster. Over here, if the potential energy is bigger, the kinetic energy is smaller. And that's what we mean by the energy being constant. The energy is transforming back and forth between potential and kinetic. Okay, this -5, -45, those are just numbers I made up to represent what we mean by a bigger value and a smaller value. As far as approaching problems with energy, if we want to relate and find a speed at a new point or how far something goes given an initial speed, conservation of energy is what we will use. Conservation of energy, again, in the test notes, they write this out where they say it is constant. What that means is all of that stuff at an initial moment in time is equal to all the same stuff at a final moment in time. Please keep in mind, you cannot use MGY for any problem that involves distances large from the Earth. Even if one moment in time is close to the Earth and another is not, we cannot use MGY. We have to use the same version of potential energy for both initial and final moments in time, which is fine. This is our equation. We just need to use it as it is. So I'm going to go through a few examples as well in separate videos. We are assuming there's no drag, no air resistance, which again may or may not be a good assumption. But again, just to keep on the more basic side of things, that's the assumption we will be making.